Okay, here we go. We are doing 2.5 Fundamental Theorem of Algebra. So we know that if we had an nth degree polynomial, that we'd have at most n real zeros. For example, let's say we had a polynomial y equals x cubed plus 2x squared plus 4x minus 10. We know that we would have at most n real zeros. So what that means for this, we would have at most 3 real zeros. I like double underlining things, don't I? 3 real zeros. But now we're going to, do I need that E in zeros? That looks kind of funny. I don't think I need it. But now, when we talk about the complex number system, we're going to improve on this statement, okay? So what this means is this. In the real number system, this is still true. We're going to have at most, whatever our highest degree is, that's how many zeros we can have at most. But now when we talk about the complex number system, which is any number that can be represented by a plus bi, we're going to have a new rule. So let's see if the new rule's here. Okay, here's the new rule. In the complex number system, every nth polynomial function has precisely n zeros. So let's look back at that same polynomial, and now we know that it actually has exactly 3 zeros. So we don't know whether they all come from the real number system, so whether they're real numbers or whether they're complex numbers. And yes, that's imaginary, right? Complex numbers are a real number plus an imaginary number, right? A plus bi. So this is pretty cool. It's like, okay, so now we know if we graph this, we might only see 1 0, but we're guaranteed if we only had 1 real zero, we have 2 complex zeros. So pretty cool, right? All right, let's have fun with this idea. Before we can have fun, we've got to look at this fundamental stuff, fundamental theorem of algebra. Okay, if we have a function, a polynomial function of degree n, then the function has at least 1 0 in the complex number system, right? Okay, that makes sense. So here's what we're talking about. If we have where n's greater than 1, so let's say let's say we have a linear. So we have y equals 2x minus 4. Okay, and when we set that up equal to 0, at x equals 2, right? We know that we have 1 0, and that happens when x is equal to 2, right? 2 is our 0. So this is crazy, right? Because it says at least 1 0 in the complex number system. And you're like, Ms. Overby, 2 is not in the complex number system. That's a real number. And you're right. And this is why I put here, we've got to remember that every real number is a complex number with an imaginary part equal to 0. So I could write x equals 2 as 2 plus 0i. Voila, it's complex. All right, do you have to know the fundamental theorem of algebra? It's kind of important, and we're going to use it a lot. And then let's look at linear factorization theorem, where basically if we've got a polynomial of n degree, where n is greater than 0, then the function has precisely n linear factors, which makes sense, right? If we have exactly n zeros, then we would have exactly n linear factors. This may be something that you want to come back to after we're done with all of our examples. Then go ahead and zoom back to this part of the video tutorial and listen to these words again. And I think it'll make a lot more sense. So let's do our examples. Example 1, find all zeros of the function and write the polynomial as a product of linear factors. All right, so when I'm looking at this, I'm like, oh gosh, do I have to do my P's and Q's? This looks confusing. And then I'm like, oh, wait a minute, this follows a similar pattern to quadratics, right? We see a 4 and we see a 2. This reminds me of a quadratic. Now I can't even see the problem, so let me get rid of those circles. What if I wrote this same function as a quadratic? Okay, so all I'm doing is I'm changing, instead of a 4 and a 2 and a 1. So I'm keeping the same proportion, but it's going to give me an idea, right? Because I'm like, oh, I can factor this, right? Two numbers that multiply to equal negative 13, but add to equal a negative 12. How about negative 13 and plus 1, right? And then I'm like, ooh, I think I can take this factoring I just did and apply it to this function that has a fourth degree. It's a fourth degree power. So instead of factoring it exactly like that, I'm going to do x squared minus 13 times x squared plus 1. If you pause this video and you distributed the x squared and the negative 13, you would indeed get back to your function. Okay, so that's just one of those tricks that we use to factor something higher than a quadratic. Well, really, we can only use it for certain types of, they have to be a trinomial, and the exponents have to be 4 and a 2, or a 6 and a 3, or an 8 and a 4, right? You get it? Okay. So we're looking for the zeros. If we want to find the zeros, we're going to set our factoring equal to 0. And we know that something times something equals 0 means that either x squared minus 13 equals 0 or x squared plus 1 equals 0. So we're going to go ahead and add 13 to both sides. We'll take the square root of both sides, and we get two zeros there, right? A positive 13 and a positive square root of 13 and a negative square root of 13. Over here, when we subtract 1 from both sides, we're going to get what? The square root plus or minus the square root of negative 1. What's the square root of negative 1? I, right? So plus or minus I. All right, so we found our zeros, but then it asks us to use these zeros and write the polynomial as a product of linear factors. Okay, so we need to do that. So this is what we're going to do. We're going to remind ourselves, all right, plus or minus 13 really means I have two zeros here, right? Either x is equal to positive square root of 13 or x is equal to negative square root of 13. Okay, and over here I have two zeros. In addition, I have x equals an I and x equals a negative I. Okay, so if I want to put these in factored form, that means that I need to subtract whatever's on the right side and bring it over to the left side where x is. It'll make sense in just a second. If I subtract square root of 13 from both sides, look what I have. Okay, if I subtract negative square root of 13, I've got this. If I subtract I, I've got this. And if I subtract negative I, I've got this. So stay with me here, because a product of linear factors basically is saying this. I've got all my factors right here. There's one. There's one. And there's one. And our very last one is this. We're really going backwards if you look at it. I could put equals 0 here. I'm going to erase that in just a second because that's not part of my answer. But think about, we're going backwards. Usually we end up with a function, okay, and we start with a function. Then we go, our next line would be factoring the function and setting it equal to 0. Then our next line would be setting each of the factors equal to 0. And then our next line would be solving for x. So actually what we're doing is we're doing that process backwards. When we start out with our zeros, because we started out knowing what our x's were equal to, we're working backwards to get to, not the function itself, because we already know what that looks like, but we're getting back to what the function looks like in factored form. That's our answer. All right. Hopefully when we practice lots of these in class, it becomes easier for you. Practice really does help, doesn't it? So example 2 says find all the zeros and write the polynomial as a product of linear factors. It's asking us to do the same thing. This time we have a quadratic, which yay, because maybe we could factor it, but boo, no we can't. So if we can't factor, we can either complete the square or we can do quadratic formula. Which one do you want to do? We can do quadratic formula. Maybe next time we'll complete the square. So we know that what a equals 1 and b equals -4 and c equals +1 and x equals -b. So -4 plus or minus square root b squared minus 4ac all over 2a. All right, so we're going to have a little bit of fun with this. Let's see, minus negative is 4, plus or minus. Let's go ahead and put that square root stuff into your calculator, and you get square root of 12. We don't want to write that as a decimal approximation. We would if we were in a context problem, but we want to keep it real. We want to keep it as exact as possible, not an approximation. So we're almost done there. We want to go ahead and that square root of 12, we can simplify, right? So we're going to have, we know that square root of 12 is the same thing as square root of 4 times 3, which is the same thing as 2 square root of 3. But we're good at that. We've been practicing that in class, hopefully. I say that. And I'm saying that in the spring before I see you guys in the fall. So I'm really hoping that you've got square roots down by now. So here we go. We're almost done, but we see that we can factor a 2 out from the numerator, right? And we want to do that because that's the only way we can cancel out the 2. We know that we would never be able to cancel out the 2 unless we had another 2 that was being multiplied by something else. You can never cancel out anything that an addition or a subtraction sign brings together. So we've got 2 zeros here, right? We have 2 plus square root of 3, and we have 2 minus square root of 3. So it's a quadratic that has 2 zeros, which makes sense. And then, so that's one part, that's one of our answers. Those are our 2 zeros. And then we want to find the product of our linear factors. And so we're going to work backwards. Remember what we did? We went ahead and subtracted. Now I'm going to subtract the whole thing. So I'm going to subtract 2 plus root 3. And I do that because I want to remember to distribute the minus sign. Okay. So there we go. We've got that, and then we're going to subtract this whole thing. So we're going to distribute, and we're almost there. How do we write it as a product of linear factors? Well, there's my linear factors. Now, could I have kept it in a different form? I could have, if I didn't distribute the negative sign, I could have just stopped and said, there's my factor, there's my factor. That's acceptable as well. Okay, so once again, I'm hoping that just seeing it helps you to understand it, but really, those that do the doing, do the learning. Hopefully you're not sick of hearing that by now. Okay, so let's talk about conjugate pairs. So we know that a complex number can be written as a plus bi, and we now are being reminded, if you didn't know before, that the conjugate of a plus bi would be a minus bi. And whenever a plus bi is a 0 of the function that we are looking at, then we know that the conjugate, in this case, would be a minus bi, would also be a 0. So let's say one of your zeros is 2 plus 3i. Well, then you know 2 minus 3i is also going to be included. That's just the deal. You can't get one complex number without the other, without the conjugate pair. Wonder if your real number was 0 and you just ended up with like a 5i. Well, the negative 5i is going to be also a 0. And of course, you could be given a negative 2i, and its conjugate would be a positive 2i. That would also be a 0. So it's kind of cool, and we need to remember that because there are going to be problems like this next one that will try to trick us. Here it's giving us our zeros and asking us to find a fourth degree polynomial. The problem is they're only giving us 3 zeros, and we know that a fourth degree polynomial has exactly 4 zeros, including the complex number zeros, right? So I'm going to go ahead and say, well, they gave me one of my zeros is a 0, and another 0 is a 1, and another 0 is an I. All right, what's the conjugate of I? That's right, negative I. So that's my fourth 0. So now that I know my zeros, I'm going to be working backwards. I'm just like I did before. I'm going to be subtracting what's on the right side. X minus 0 is 0. So that was kind of interesting. So I have x minus 1, x minus I, and x plus I. Then I continue to work backwards, and I drop the zeros. I'm going to write them just as a product of linear factors. And then I'm going to, actually I don't need the equals 0, but I'm going to go ahead and distribute. Honey, it's on my desk. I'm going to go ahead and, because they didn't ask me to write it in factored form, they asked me to actually write the function itself. So I've got to continue. And so what I'm going to do is I'm going to distribute, switch colors. I'm going to distribute that x. I'll have x times x is x squared. X times 1 is negative x. So I'm going to keep that. And then I'm going to go ahead and multiply these conjugates, because we love multiplying conjugates, right? Because look what happens. X times x is x squared. And yeah, the outer and inner, you got it, they're going to cancel out. That's why we love multiplying conjugates. And that's why we do that so often. So then we're going to have... let's see, so we'll have x squared minus x, and then we'll have x squared, and my two outer and inner terms cancel out. And then I've got minus an I squared, which I know that I squared is a 1. So I'm sorry, an I squared is a negative 1. So minus a negative 1 is a positive 1. Okay, I've been doing too many tutorials in a row. Let's go ahead and switch up colors again, and let's distribute again. So we'll have x squared times x squared, which is x to the 4th, and then x squared times 1 is x squared. Negative x times x squared is negative x cubed, and negative x times 1 is negative x. Are there any like terms to combine? No, let's just get it in descending order so it can be in the proper form. Whew! There we go. This is the function that has the 4 zeros of 0, 1, I, and negative I. There it is. Quite impressive. We can do that. All right, example 4. Is this my last example? Yep. Find all zeros of the function and write the polynomial as a product of linear factors. So I'm looking at this, this cube, and I'm like, oh, darn it, I can't set up my 2 parentheses and factor. I've got to do my p's and q's, right? So I've got that my p, let's see, the p's are all of the factors of negative 7. So what I've got plus or minus 1 and plus or minus 7. And q is just plus or minus 1. So if I do p over q, I'm going to get what? Plus or minus 7 or plus or minus 1. Who do you think I'm going to pick first to do synthetic division with? That's right. I'm going to try the 1. So I'm going to set up synthetic division where I've got a 1. I've got to be really careful. I don't have an x squared term, so I'm going to put a 0 for the coefficient for the x squared term, then a 6 and a negative 7. Drop the baby, and the baby says, ma, ma, ma. That's terrible, isn't it? Don't ever drop the baby. Okay, so 1 times 1 is 1, and then we're going to add, and 1 times 1 is 1, and we're going to add, and oh, that's beautiful, right? We know that when we get 0 in the remainder spot, that we have a factor. So we know one of our factors is 1. So we're going to go ahead and write that down here. X equals 1 is a factor. And then we know that this 1, 1x means that we're left with, let's do it in red. That means that we're left with x squared plus x plus 7. So that means when we divide x cubed plus 6x minus 7 by x minus 1, this is what we get. So we got to keep working. This is one of our zeros. We're going to find the other two because we know that we have exactly 3 zeros if we count the complex zeros that are available to us. Can we factor this? No, boo, we can't. Let's use the quadratic formula. We could complete the square, but I've got work here for the quadratic formula. I'm going to use that. All right, so we know a equals 1 and b equals 1 and c equals 7. So x equals negative b plus or minus square root b squared minus 4ac all over 2a. Can't write the quadratic formula without singing that. So sorry, you're going to have to put up with that whenever we have the quadratic formula. So here we go. We're going to realize real quickly that we're going to have a negative underneath our square root sign. And so what we're going to do is this. We're going to simplify our 0. We know we're going to have a complex 0, right? We're going to take that root 27 and remind ourselves that that is the same thing as root 9 times 3. Square root of 9 is 3. That gets to come out. But oops, let's make that 9 times a negative 3. So we're going to rewrite this as negative 1 plus or minus 3, and then the square root of negative 3. And then we know we can write that as plus or minus 3 square root of 3i. Make sure that your I stays clear of that radical sign, right? It is not underneath the radical sign. So let's see, it wants to know the zeros. So we already know, let's see, this is going to give me 2 zeros, right? Either negative 1 plus 3 root 3i over 2, or the other 0 is x equal negative 1 minus 3 root 3i over 2. And then let's not forget our 0 from way up here from synthetic division, x equals 1. That's our other zeros. So look at that. We've got 3 zeros, just like we were contemplating in the beginning of this tutorial. Counting complex numbers, we will have exactly the amount of zeros that our highest exponent is equal to. All right, so here we go. We're not done, right? Because they asked us for the product of linear factors. All right, here we go. We're going to go ahead and subtract 1. So there's one of our factors. And let's go ahead and subtract this whole thing. I am not going to distribute the negative sign. I'm going to keep it like that. And let's go ahead and subtract this one. Whew. And we're done. This is in the red were the zeros, and in the blue are the product of linear factors. Whew. Thanks for staying with me. I look forward to practicing these in class with you because practice really does make perfect. See you in class.